Hi everyone. It's a pleasure to be here. I want to start by thanking the organizers for inviting me for such an interesting event. I'm really looking forward to having fun discussions with all of you. I thought that today it would be interesting to tell you guys about a line of research that we've been developing for the last few years. And because of the nature of the event, which again, it's really cool, I thought that I would allow myself to speculate a little bit and try to draw some connections between this line of research and neuroscience. So I'll have the talk in three parts. The first part, I will give you the concept of generalized policy updates. In the second part, I'll tell you about some experiments to make the concepts more concrete. And then finally, I'll try to connect these concepts with neuroscience. Cool. So what are generalized policy updates? As we all know, value-based reinforcement learning is based on two basic operations, policy evaluation and policy improvement. And pretty much all algorithms can be understood as small variations of these two operations. So what I will do here today is briefly give the concepts of policy evaluation and policy improvement, and then I'll generalize them. Okay, so we start with a policy by one, and as a reminder, a policy is a mapping from states to actions. Now, we can compute the value function of this policy, and the value function is essentially the expected discounted sum of rewards from a given state. And here you can see that I'm using a subscript R because I'll be talking about different tasks. And for the purpose of this talk, a task is simply a reward function. Okay? So this object then is the value function of policy pi1 on task R. And this process is called policy evaluation. Why do we do that? We do that because once we have the value function of pi1, we can compute the second policy, pi2, which is better, at least as good as, but in general better than pi1, in the sense that it's going to do at least as well, if not better than pi1 from every single state. And this is called policy improvement. So now we have these two operations, policy evaluation and policy improvement, and we can alternate between them. And if we keep doing that, we will eventually get to the optimal value function of the environment, from which we can derive all optimal policies of the environment. Cool. So we can see that we have two spaces involved in this process here. One is the policy space, where the policies lie. The other one is the value space, where the value functions lie. Now, I'll ask you to pay attention to the policy to the value space, and I'll make the assumption that this is a two-dimensional value space. So we essentially have two states only, and the value function in this context is going to be just a two-dimensional vector. Nothing I'll tell you today depends on this assumption, obviously, but this is just to make things easier to illustrate. Okay, so how does this alternation between policy evaluation and policy improvement reflects on the value space? So for example, let's say that we have computed the value function of pi2, and you do policy improvement. This means that the value function of the next policy will have to be in the blue region, shown here. Right? It's contained in that space. And similarly, if we do the same with pi3, the next value function will have to be in the darker blue region. So one way of looking at this process of doing policy evaluation and policy improvement is that we're kind of squeezing the value function to the top right corner of this space, which is the optimal value function. So you're getting closer and closer to being optimal. Okay? So now, how do we generalize these concepts? So the first thing I'll tell you is generalized policy improvement, or GPI, which is as follows. We have a policy, and again, we have the value space, the two-dimensional value space, and now we compute the value function of this policy, and we get a point, a vector, a two-dimensional vector. Now I do the same for another policy, and if we do the same exercise as before, if I were to do policy improvement based on the value of pi1, the next value function would have to be in the blue region. And the same applies to v of pi2. But now, GPI, Generalized Policy Improvement, or GPI, you compute the next policy based not on a single policy, but on a set of policies. So, and the result of that is that the next value function will have to be in the intersection between the two regions. So you're making it even more restrictive. So this is called Generalized Policy Improvement, or GPI. And obviously, because the next value function will have to be in the intersection, if we have more policies, we can only decrease the size of the intersection, right? So if you add, for example, another policy, pi3, compute its value function, see its improvement space, and compute the intersection, we end up with a smaller intersection. Okay? So this is GPI. Now, a valid question here is that to define this navy region, I had to do 3 policy evaluations. And as we all know, policy evaluation can be quite costly. So it's a reasonable question to ask, why not just do the usual value, policy evaluation, policy improvement alternation? And the answer to that is that GPI is really useful when combined with a second concept called Generalized Policy Evaluation, or GPE. Because if we combine these two things, these two operations, which are generalizations of the two basic operations of value-based RL, then we can do zero-shot. We can compute a policy that will do reasonably well on a potentially infinite set of tasks. So let me show you how. So here we have policy pi1, but instead of having a single policy, we have a single task, we have 3 tasks. And again, I'm assuming the two-dimensional space. Now, generalized policy evaluation, or GPE, is the process of computing the value function of a policy across a set of states. So in this case, 3 states. So this is GPE. And just as a quick parenthesis, I think that most, if not all of you, probably have heard of the successor representation. The successor representation is a special case of GPE. In the past, we generalized successor representation to successor features, which replace states with features, and GPE is a further generalization. So both the successor representation and successor features are special cases of GPE. But going back to the main discussion, we have a policy. We use GPE to compute its value across many tasks, in this case 3 tasks. How is it combined with GPI, Generalized Policy Improvement? Suppose we have a second policy, pi2. Now we evaluate this policy across tasks. And now if we do the same exercise as before, we compute the regions, improvement regions. Now we know that the GPI policy will have to be in the dark blue region across all the tasks, which means that if you apply GPE and then GPI on any task, we immediately get a policy, zero-shot, without any learning, that we have to perform in the space of the dark blue. Cool. So this is general, and the GPE and GPI together, I call them generalized policy updates. Cool. So now I'll tell you about some experiments we did in the past, just to make these things a little bit more concrete. So in this experiment, we have a grid world. We have 2 types of objects. We have red squares and blue triangles. And then we have different rewards associated with object types, not individual objects, but object types. And now the rewards will change across tasks. So a task here will be a specific reward associated with squares and a specific reward associated with triangles. And then I'll define some training tasks, which will be essentially how much reward the agent gets when it collects a square or when it collects a triangle. And because these tasks can be defined by two numbers, I will just put them on this arc in the following way. So for example, the task where the agent gets 1 unit of reward when it gets a square and 0 when it gets a triangle would be in this position. The opposite task would be on that position, and so on. So now I'll define 5 training tasks, which have different rewards associated with each object. And then I'll also define the test task, which is essentially all possible points along this arc. So I have an infinite test task. One last point is that performance here will be the distance to the center of the arc. So for example, an agent whose performance coincides with the outer circle would be essentially optimal across all test tasks. An agent that has this performance to the inner circle is a little bit worse, and so on. Okay? So these are the results we actually have. Let me try to break it down for you. First, pay attention to the dotted line, the dotted curves. These are the performance of Q-learning with increasing amounts of data. So if you look at the outer circle, this is the best one can do if you run Q-learning for a long, long time. So it's essentially optimal here. Now, I call your attention to the red curve. In this case, this is the performance of GPE and GPI when using a single policy, policy pi4. So as you can see, on the task pi4 itself, GPE and GPI does pretty much optimally, but this is expected because pi4, the task associated with pi4, is indeed in the training task, in the training set. As you move away from pi4, performance slowly drops, but you can actually be quite far from pi4 and do reasonably well. Now, I'll ask you to look at the green curve, which is GPE and GPI using two policies, pi4 and pi2. Now you can see that the green curve contains the red curve, and what it means is that it can actually do optimally across a larger number of tasks, so this is the test set, right? And so on. So if you look at the yellow curve, you see that it pretty much coincides with the outer circle, meaning that by learning only 5 policies, you can act optimally in this space that is the infinite space of tasks. And in case you're wondering why the negative quadrant doesn't have any tasks, it's because a task where both objects have negative rewards associated with them is not interesting. The agent can just sit still, and it's an optimal solution. Cool. So up until now, I've talked about things that we did in the past and that I know what I'm talking about. Now I'll allow myself to speculate a little bit and connect these things with neuroscience. And I'll put forward the following hypothesis. I'll suggest that an agent, a biological agent, say a rat or something like that, will do essentially 2 things. It will first remember things that were useful in the past. So the agent will only remember policies that were solutions to previous tasks. And the second point is that when the agent is faced with a new task, it will combine the solution of previous tasks, so behaviors that it did remember, it did record, by sticking them together as like Lego pieces, Lego blocks. And it's exactly for the second step that GP and GPI can be useful, because essentially what the agent will do here is that at each step, essentially the agent will ask in a given state, how well will behaviors from the past, behaviors that I remember because they happen to be useful, do on this task, on this state, and this task? And then the agent will pick the one that looks more promising. And then he'll take one step and repeat that. That's the hypothesis I'm suggesting. But in the spirit of being consistent with experiments, I'll also suggest an experiment that can either provide evidence in favor of or against the hypothesis I'm putting forward. In the experiment, it's very simple. You have a maze. Here you have two types of objects, as before, the blue objects and the yellow objects. If you look at the dotted lines, these are doors. If the agent goes through one of these doors, it cannot go back. And you can define different tasks by attaching different rewards to the two types of objects. Okay, so for example, in this task here, you have the yellow object gives the agent rewards, and the blue object doesn't give any reward. And in this case, the best thing for the agent to do would be to do right. That's the optimal policy in this case. And analogously, if I define a task that only rewards the blue objects, the optimal solution is to do left. Okay? So suppose that we now do define these policies, we design this policy, and we actually, these two tasks, and we actually run this experiment. So we call these the training tasks. And now we have a test task where the agent is rewarded by both types of objects. Okay? So let's say we have a rat, or many, and we've trained them on the training tasks, and now we expose them to the test task and see what they do, right? So I can see three types of outcomes for these experiments. The first one is that the agent will indeed find the optimal solution, which in this case is to do left and then straight ahead. This would be evidence against what I'm proposing, because this would mean that the agent does remember behavior that wasn't useful, because in the training tasks, going straight ahead was never useful. And in this case, the agent would get 7 units of rewards. The second type of outcome is one in which the agent falls back to one of the two policies learned during training. So I call them model free because in this case, the agent remembers the behaviors, but it doesn't stitch them together. It just essentially goes back to being one of the two behaviors learned. That would also be evidence against the hypothesis I'm suggesting, because they're not combining, the agent's not combining behavior. The third type of outcome is the GPI, is the one that would provide evidence for GP and GPI, because in this case, the agent would use previous behavior, only behavior that was useful before, but it will stitch them together. And if you look at this result, it would give 6 units of rewards, which is intermediate between being fully model-based and being fully model-free. So this is a summary of the possible outcomes. And essentially, we haven't run these experiments. I have no idea what would happen, but it's just, I thought that this was a good place to propose a fun discussion like this. And that's all I have. Thank you.
Thanks for the talk. I think I have a basic confusion you could probably clear up quickly. In your cartoon initially, it seemed that you were looking at a multidimensional state space where the, say, value of S2 was monotonically increasing regardless of value of S1, which allows you to always close in on a better overall value. It seems like that wouldn't generally be the case, and how do you proceed otherwise?
So it is the case in general. as long as the way you represent the value function is tabular, so it's essentially independent. So I'm talking here about the dynamic programming case where a value function is indeed a vector, and then in this case, you can always increase the value of one state independently of the other ones, right? So, and that's exactly what the theory tells us, that every time you do policy improvement, the value of at least, if the current policy is not optimal, the value of at least one state will have to increase. But you're right that in practice, we use approximation, and then the value of states are entangled with each other, and then in that case, it might not be possible to do that. You're right in that sense. But I meant in the kind of idealized case where we have values represented as independent elements of a vector.
Yeah, I think it's on the same line. Is it clear that you would always find the policy at the intersection of two of them? Because if I think of crossing a maze, I can follow right or follow left, but those two do not interpolate.
So the policy itself is not the intersection of the two. The value of the policy is at the intersection of in the value space, right? So think of the case where you have a single value function. Is that case should be clear that then you have the...
Yeah, but when you look at an intersection of the values, then you need to combine the policies.
So, okay, maybe I should have given the expression of GPI. So let me describe it to you. I tried to do this without using any equations, but let me try to describe it in words, and then I think you see it. So the first thing is that we don't actually use the state value function, V. We use the action value function, Q. And I used V here because otherwise we wouldn't be able to see the two-dimensional space. So when you do policy improvement using Q, you do essentially argmax of A, of Q as A on a given state, right? Okay. When you do GPI, you do the same thing, but instead of doing an argmax with respect to Q, we do an argmax with respect to a max over the Qs. So it's argmax A max I Q I S A. Sorry, I should have this slide. But I can yeah, we can talk offline.
Hello, thank you. Yeah. Thank you for the talk. I'm a little bit confused about how this is not leading to a catastrophic forgetting of values again of the states, because you're changing the value of the objects at each different task. Wouldn't the agent just learn a summary statistic of that object across tasks?
Okay, good. So the answer is no, but it's a little bit more involved in that. So what we need to do here is, because again, I'm hiding a few details to make things more palatable. But you have, when you do the GPE, Generalized Policy Evaluation, so if you compute the value of the previously learned policies on the new task, and then when you do something like successful representation of the successful features, which is a generalization of that, what it means is that you find a specific way, a specific weighting of the dimensions of, say, the features or the states. And the process of learning these weights can itself take a few iterations. So you either assume that someone tells you, so there's two possible scenarios. Let me be very clear, two possible scenarios. The first one, I tell the agent, look, now squares give you this much, triangles give you this much. And the agent immediately knows the value of all the policies on this new task, right? That's one scenario. The other scenario, so that's clear. The second scenario is when the agent is not told anything, but it interacts a little bit with the environment, and in doing so, it understands the value of objects, and then we're back to the first scenario. And even though you do need a little bit of learning in this case, you only need very few iterations to figure out what the value of states are. So it's like much faster than reinforcement learning in general.